The tiny bits that make up you, your bones, your skin, everything, were actually created inside huge stars that blew up billions of years ago. But how did those stars come to exist in the first place? What exactly happens during their lifetime before they scatter their ashes across the universe? Let's find out. The cosmic nursery. Every star out there, including our very own sun, starts its life in a place called a stellar nursery. Sounds cute, right? But it's actually a massive cloud of gas and dust drifting through space. We call it a nebula. You've probably seen those colorful NASA images that look like digital art. But those glowing clouds are actually star-making machines. These clouds might look still from a distance, but they're active, dynamic, and full of potential. Within these cold, dense regions, gravity starts pulling tiny particles together. Slowly, clumps begin to form. They grow, drawing in more material as they go. It's a gradual buildup, but one that never stops. The more material that gathers, the greater the pressure at the center. And with pressure comes heat. Temperatures start climbing steadily. At a certain point, the core gets hot enough to glow, faintly. A deep, reddish light appears at the heart of the clump. That's when we call it a protostar. It's not a true star yet, but it's definitely on its way. These early clumps vary in size, and not all will become stars. Some may become brown dwarfs. Failed stars that never ignite fusion. But the ones that do keep growing, feeding on the nebula around them like newborns taking their first breath. At this point, the protostar is surrounded by a swirling disk of leftover material, much of which might eventually form planets, moons, or comets. The surrounding cloud is turbulent, full of shockwaves and bathed in infrared light, completely invisible to the human eye without special telescopes. Over time, as the protostar grows, it begins to settle, shedding its cocoon and stepping into its identity as a newborn star. Birth of a star. This protostar keeps collapsing, getting hotter and hotter. The pressure and temperature at its core become absolutely immense. And then, something incredible happens. When the core reaches about 15 million degrees Celsius, which is about 27 million Fahrenheit, nuclear fusion ignites. Now, you might be wondering, what exactly is nuclear fusion and why is it such a big deal? In the intense heat and pressure at the center of the protostar, hydrogen atoms are moving at such high speeds that they begin to collide and stick together. Specifically, 4 hydrogen nuclei fuse to form one helium nucleus. But when they fuse, the resulting helium nucleus has slightly less mass than the 4 hydrogen nuclei that formed it. That missing mass doesn't just vanish. It gets converted into pure energy. Thanks to Einstein's equation, E equals mc squared. And that energy is enormous. It radiates outward from the core as light and heat pushing against gravity and causing the star to shine. This moment marks the birth of a true star. It's no longer just collapsing gas, it's now a self-sustaining nuclear engine. This fusion process creates an outward push of energy that perfectly balances the inward pull of gravity. It's a cosmic tug of war, and for billions of years, the star is in perfect balance. This is the longest stage of a star's life, called the main sequence. Our own sun is a main sequence star, happily fusing hydrogen into helium right now, and has been for about 4.6 billion years. It's in its prime. The color of a star on the main sequence tells us something about its size and temperature. Big, hot stars burn through their fuel much faster and glow blue. Medium-sized stars like our sun are yellow, and smaller and cooler stars are red. And it's not just about color. Blue stars may only live for a few million years, while red dwarfs can shine for hundreds of billions. That's longer than the current age of the universe. This phase is incredibly stable, and it's during this time that stars can host entire planetary systems, possibly even life. If we look at the stars closest to us, Alpha Centauri, Sirius, and Proxima Centauri, many are main sequence stars, still burning brightly in their cosmic adulthood. The midlife crisis. But nothing lasts forever, not even stars. After billions of years, a star like our sun starts to run out of hydrogen fuel in its core. It's like a car running low on gas. When the hydrogen in the core is mostly gone, fusion starts to slow down there. Gravity begins to win the tug of war, and the core starts to shrink and heat up even more. This extra heat causes the outer layers of the star, which still have plenty of hydrogen, to expand dramatically and cool down. the star puffs up into a colossal red giant. It can swell so much that it would swallow Mercury and Venus, maybe even Earth. Our sun will become a red giant in about 5 billion years, and yes, it will engulf our planet. Don't worry, just subscribe to our channel to make sure you won't be around when the sun explodes. At this stage, the inner core is now fusing helium into heavier elements like carbon and oxygen, but it's unstable. These reactions don't last nearly as long. The outer layers balloon outward and pulsate, shedding mass into space. The sun's solar winds would become thousands of times stronger, stripping nearby planets of their atmospheres. Any satellites or probes we've sent out will be vaporized in a snap. Eventually, the outer layers drift off, leaving behind a hot, glowing core and clouds of material floating into space. A farewell gift to the cosmos. This marks the beginning of the end. Death of a star. And now, after the explosion, what happens next depends on how massive the star is. For sun-like stars, after their red giant phase, they can't hold onto their outer layers anymore. It gently sheds them, creating a beautiful, glowing shell of gas called a planetary nebula. These aren't related to planets, they just look like them through a telescope. The core that's left behind is super dense, extremely hot, and about the size of Earth. It's now called a white dwarf. It slowly cools down over billions of years, eventually becoming a cold, dark black dwarf. Even though none have been observed yet, as the universe isn't old enough. The white dwarf still glows with leftover heat, but there's no more fusion happening inside it. It's the stellar equivalent of embers in a dying fire, beautiful, fading, and silent. Over time, it stops glowing altogether, becoming invisible against the black of space. Even though it's no longer active, this remnant core contains nearly all the mass of the original star, compressed into an object no bigger than our planet. It's like squeezing the mass of the sun into something the size of Earth. But if a star is much more massive than our sun, let's say 8 times bigger or more, its death is far more dramatic. Instead of gently fading, these giants go out with an unimaginable bang called a supernova. The explosion is so powerful that it can outshine an entire galaxy for a brief time. During a supernova, elements heavier than iron are forged and then blasted out into space. And what's left behind? If the core is incredibly dense, it collapses into a tiny, super dense object called a neutron star, literally, a star made mostly of neutrons, where a teaspoon would weigh billions of tons. Some neutron stars become pulsars, cosmic lighthouses that spin rapidly, shooting beams of radiation. Others become magnetars, with magnetic fields so strong they can disrupt electronics from light years away, though luckily none are near Earth. But if the star was truly colossal, even the supernova couldn't stop the collapse. The core implodes with such force that it creates a region of space-time where gravity is so strong nothing, not even light, can escape. This, ladies and gentlemen, is a black hole, a cosmic trapdoor from which there is no return. Black holes don't just pull in matter, they also bend space and time itself. They may sit quietly at the center of galaxies or consume entire stars in violent outbursts. We've even photographed one, the shadow of a black hole in galaxy M87, a real image captured by a global network of telescopes. And perhaps most incredibly, some scientists believe supermassive black holes may have influenced the formation of galaxies themselves, shaping the structure of the universe. So, the next time you look up at the night sky, remember, those tiny lights aren't just points of light. They are living, breathing cosmic furnaces, born in nurseries of dust, shining for billions of years, and then, in their dying moments, creating the very elements that make up everything around us, including you and me. We are quite literally made of stardust. What an incredible journey, right? If you like this video, make sure you subscribe to our channel to find more interesting videos like this one.